Good morning, everybody. This is going to be the third PowerPoint for the week, and it is PowerPoint number 52 on AC drive troubleshooting. So the last couple of PowerPoints have been over installation and optimization of the power of the AC drive. This one's going to be over fixing it or trying to identify what's wrong with it. So let's get started. Today's objectives, should you choose to accept them, are to describe the installed AC drive system hardware. The hardware being what you need to facilitate getting the current from the breaker panel to the actual drive and then actually to the motor. So the actual hardware stuff. Describe the operation of an AC drive motor control system. List the potential problems related to an AC drive system installation. Localize and isolate AC drive component problems, and list the test instruments necessary to troubleshoot an AC drive. Like I said, my rule of thumb, or the way that I was always taught, is that you really don't do a lot of it troubleshooting with drives that are less than 100 horsepower. You just throw them in the trash. You might have to figure out if it's the motor or the drive, which is pretty simple. If you unhook the motor and you let the drive run and the drive still trips out, then it's the drive. If you unhook the motor and the drive doesn't trip out, it's probably not the drive. It's pretty self-explanatory. So let's keep going here. This kind of lists what the hardware is and what the potential problem areas can be. When you open up a cabinet or you open up one of these MCC boxes or MCC buckets, you're going to sometimes see a lot of different stuff running around, and it can be quite intimidating. Most people that start in on this journey of industrial electricity, the biggest reason why they struggle, or one of the biggest reasons why they struggle, is that they can have just anxiety or lack of confidence is one of the big reasons. When you open up one of these cabinets and you see a gajillion miles of wire inside of them, it can be a little intimidating. And if you're not confident that you know what you're doing, obviously don't stick your hand in there. But developing that confidence can be the majority of the problem with people. So if you're looking at this, I'd really what I would like is to call your attention to the left-hand side right over here. If you break it down to what it is, yes, this can be intimidating. It is very intimidating. But if you break it down to what it actually is, it's a pretty simple circuit that goes from whatever power source you have. Let's say the pole, right? You're going to have a pole out here with some sort of power. If we were in our building, it would have 4160. 4160 pole right here. It goes in, and it goes from the 4160 pole into a transformer, actually. So let's 4160 pole goes into a transformer. And I'm just going to put a box with a transformer. That transformer is going to drop it down to, usually it's 480. But then ultimately it ends up down here at 208 volts, three-phase. In our shop, we have 208 volts, three-phase. Why? So that comes into a disconnect. If you were in the upstairs shop, in the motors and drives shop, that disconnect would be the one that's powering the breaker panel. Let's just call it that. ultimately, we end up on the three-phase panel, and we have a disconnect on your three-phase panel, and we don't have fuse disconnects, but you would have a fuse disconnect sometimes not. That could be optional. So let's kind of run down through this and see what we got. The first disconnect or bypass system for the thing is so I can shut down the entire circuit, right? If I want to shut down the entire circuit, how do I do it? Well, in our lab or in our shop, it would be the big breaker panels that are on the wall. So you could go over and shut off those breaker panels and kill all the power going to all of the three-sided panels. So if I have voltage here, and that's what we're talking about here, is trying to troubleshoot these drives. It's kind of a place where you can lose voltage, or a place where you can measure voltage. Ultimately, it ends up down here. This right here, if you look, is called the bypass. And the bypass is there so that we can turn off the drive and we can run the motor just on its own power. So, for instance, if the drive goes bad, we might be able to just turn that motor on and run it as an emergency purpose, or we can run it on the bypass just to see if it's the motor, to isolate whether it's the motor or the drive that's giving us trouble. And that's kind of the way you would eliminate it or troubleshoot it. Apply the KISS principle. Anybody knows what KISS stands for? KISS stands for Keep It Simple, Stupid. Or Keep It Simple, Students. Whichever one you want to. I prefer the stupid one, but since you're students, keep it simple, right? Develop a plan. You've heard me say this before, and you'll probably hear me say it again. You plan your dive, you dive your plan. You go into this, you need to figure out what tools you need, what PPE you need, what permissions you need. If you have to go out onto the floor, you have to have a fire watch, you have to have managerial permission to be out in the shop or where you need to be. So you have to figure out something along the lines of permission and PPE and tools. The other thing you need to figure out is what you're going to have to test in order to make this thing work. So, second thing is to localize the hardware. Localizing the hardware means that you figure out where the power is coming from, what's controlling it, where the drive is, and where the motor is, and what is the motor doing. Sometimes it can just be as simple as there's a blown fuse, and fuses blow, and you pop them back in, and they never blow again for another 20 years. Sometimes it's more complicated than that. Don't make it any more complicated than it needs to be. Sometimes the motor is tripping out and the drive is tripping out because there's something wrong with a conveyor. There's a mechanical system, a bearing, a chain, a cog. Something is going out that we have no control over. So you need to kind of be able to isolate them to try to figure out which one is the culprit. And it's probably going to be one of these 5 things: the power, the control, the AC drive itself, the motor itself, or what the motor is trying to push. If you got a big gigantic pump that's going out, the motor could be tripping out because it has to work too hard. But it's not necessarily the motor and drive's fault. It is the fault of the pump itself. The next thing, we check power. Make sure all the AC line power conditions are met. We want balanced 3-phase. We want the correct amount of voltage within a couple of percentage points, and we want as clean and as non-harmonic power conditions as we can get. After you've checked that, check the fault codes on the front of the drive. And without having actually been in the shop to actually touch a drive, this is going to be a little bit more difficult than you think. Sometimes it can be as simple as the thing's just flashing at you, and it's telling you what the fault codes are. But sometimes if people have eliminated the fault codes, you have to go back into the fault history and pull them back out of the memory of the drive. So it's not as easy as it sounds, but if you can pull the codes out, you can figure out what's wrong with it normally. If some codes can be really ambiguous though, and we're going to talk about that when we get in the shop, because you'll kind of get a code that says an overvolt. Well, overvolt can mean 100 different things. It could have just saw it for a split second and now it's gone. It could have been those reflective waves we talked about yesterday. It could be capacitive charging happening, or it could have just been a weird anomaly that the drive picked up on, and it never happens ever again. So you don't necessarily have to put them for face value. Sometimes there's an underlying issue or underlying cause. So what is the plan? What kind of PPE do I need? Like I said, what kind of tools do I need? What kind of test instrument do I need? And you notice I use the word proper tools. That means if I need a hammer, I bring a damn hammer. It means if I need a screwdriver, I bring several screwdrivers of the right sizes. I don't try to cram my panel screwdriver into a big honking flathead screw and I break my panel screwdriver, or I round out the screw. If I need a Phillips screwdriver, I use a Phillips screwdriver. Determine what, where, and how to make safe validation tests. So this kind of goes along with the things we've talked about before, opens and closed, right? Open and closed, open and closed. If I measure across this disconnect with the arm closed, I should see 0 volts. If I measure across this disconnect with the arm open, I should see all the volts, or quite a bit of voltage, right? So again, if you work in one of those shops that allows you to check with voltage on to do hot work, then you should be able to test all of these points. Each one of these things, once you have identified these points that need to be tested, these validation points, you can check across the fuses. You can check across the drive. You can check across a contactor if there is one down here, and you can check across the motor windings or the overload relay. Usually this stuff here is it can be part of the control circuit or it's part of the drive itself. Sometimes they're internal to the drive itself. So you localize the power. Localizing the power means just figuring out which one could be the culprit. It's got to be one of, if this is the only thing that comes from the pole, right? If this is what's coming from the power source, from the transformer or the pole, the only thing it could be is one of these things. And you start with the simplest thing first. Is the disconnect arm closed? Well, yes, probably. But let's go check it. Is the fuses good? Yes. The AC drive? Well, something's going on there. We'll check the codes. We'll do some stuff. The AC drive output contactor. Usually, like I said, this is internal. But this will be based on whether or not our control circuit, our stop, e-stop, stop, start, right? All of that is going to be ran into the drive and is going to be controlling these two things. Not necessarily controlling the overload, but as part of the overload circuit and as part of the control circuit for our push buttons, our toggle switches, our whatever the case may be, our automation controls. So if you have a problem with things down here, these things down here, you might be having a problem with your automation system. You might have a bad photo eye. You might have a bad proc switch that's not letting it go. But by the time you get down to this point of troubleshooting, you've already made sure that you have power going to the drive, you have good fuses, the drive is functioning as best as you can figure, and you've checked the codes that are coming out of it, and there's nothing major. Then you check the control. If all of this is working, that motor should turn on. If it still won't turn on and all of this is working, I can tell you it's probably the motor or the load itself. Now, in a lot of places, it wouldn't be up to us to go check the motor itself or the load that's on the motor. That would be a mechanic's job. We've identified that it's nothing in our realm of expertise. It's not the motor, it's not the overloads, it's not the contactors, it's not the drive, it's not the disconnect, it's not the fuses. This is a mechanical issue. That, whatever, the coupling that attaches the motor to the pump is broken. Yeah, the reason the pump isn't pumping is because there's a coupling broke, or the shaft broke on the pump. Not my job. Sometimes it'll be your job, depending on where you go to work, but in bigger plants, they have a separate crew that fixes that. So common issues or common problems that can arise from use. The nominal supply voltage. We've talked about the nominal supply voltage before, how we can have varying voltage levels, varying current levels, unbalanced transients, harmonics. The harmonics are in there because they're coming from Ameren or Southwestern Electric or whoever. And you can have all of these problems before it even gets into your circuit. Voltage unbalance can cause a real big problem with the DC bus as well. If you have a big voltage unbalance, you're going to get different peaks, which is going to cause different spikes on your DC bus. You're going to end up with either too low a voltage or too high a voltage coming across your DC bus. Once you get to the IGBTs, this output, this AC, DC to AC output right here, the inverter we call it, the inverter, really the only thing that can go wrong with the inverter is either the control isn't telling it to shoot, which means it's an internal problem with the drive, or one of the IGBTs has gone bad, or there are harmonics in the lines that are causing problems. Again, less than 100 horsepower, we're just going to say the drive is junk, and we're going to pitch it and get another one. For the most part, that's all we can do. By the time we try to troubleshoot one of these little drives, if you can even access the parts with the little drives to check them, you're not going to have a lot of success. So the next thing would be the cables. If you're getting interference in the cables, like I said, that was some of the stuff we were talking about yesterday. The whole capacitive charging and transient voltages and harmonics and things like that on those cables can be causing problems. Is there a reason why you're getting what you're getting on the motor? The motor, we've talked about bad things going on in the motors. The motor's being overloaded. It's single phasing. It's been having trouble. So you can check the motor then. In my experience, the motors don't go out very often. If they're treated correctly, if they're kept clean, if they're maintained properly, the motor will last for 50 years. If it's being abused or it's being used for something that it's not supposed to be being used for, it will die pretty quickly. And then the mechanical outputs. In my experience, it's usually right here on the mechanical side, or it's back up in here on the Ameren side. The only thing that can stop it then are the little things, right? The actual control circuits. The control signals are the only other thing that can keep it from going. The drive isn't putting out power. because somebody hasn't pushed the button, or somebody already did push the button, or somebody pushed the button at the wrong time, or the button is broke, or the switch is broke, or the photo eye is out, or the proc switch is out. This stuff they make pretty indestructible. Not that it can't be broken, but there isn't a lot to it. It looks confusing and it looks like it could be very fragile, but it's really not. This thing is pretty grenade proof. If you get good drives to begin with and you get good stuff, good parts, you won't have a lot of trouble. So first thing to do is check the power. Always check voltage first. That's what we've talked about. Checking voltage, checking voltage, checking voltage. And if you disconnect the AC motor, you can actually mag the motor, but disconnect it from the drive. We do not want to get a spike into our drive. That'll zap those IGBTs quicker than anything. So make sure either you have an output contactor that you can disconnect from the motor, or disconnect the entire circuit from the motor. Once you've disconnected the motor, it's fine to check the motor with a mag. It's fine to do any of the other checks that you want to do. But the output side, the IGBT side of your drive, you need to try to protect it from transient voltages. Check the fault codes of the drive. That, when we get into the shop finally and we start talking about doing troubleshooting on these drives, trying to figure out what's going on, I'm going to show you how to do this and kind of how to do it in a methodical way. For now, just understand that you need to check the fault codes. This will sometimes point you right to the problem. Sometimes, like I said, it can be really ambiguous, and it'll just say DC bus voltage. It won't even say if the DC bus voltage is too low, too high, or anything. It just says DC bus voltage. And you're like, well, what do I do now? Some manufacturers will give you a troubleshooting step-by-step troubleshooting manual for each major fault code. So it'll say like fault 10, and it will tell you to check the incoming voltage. And then if you have good incoming voltage, we'll then check this. And then if you have this, you have good whatever voltage at the top of the drive, then check the bottom of the drive, and then put it in manual mode and turn it on and see if it goes. And it'll tell you, or it'll tell you to up the current setting or something like that to see if you can get it to run. A lot of times the fault codes are really ambiguous though, and whatever. Troubleshooting the AC drive is divided into 3 sections. Check without the power. So to check without the power is usually checking continuity. Check it with an ohm meter, make sure there's no power applied, and see if you have continuity anywhere that you shouldn't have continuity. Check and make sure that you have continuity where you should have continuity. The other thing you can do is, with the power off, you can check the IGBTs just like a normal diode, but that's kind of a last-ditch effort to me. Turn the power on and then check for voltage. Voltage, 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 voltage. If you don't have fuel, if you don't have power, you're not going to go anywhere. And then check the fault codes. Checking the fault codes usually just explains what the fault condition was. It doesn't. Some of the newer drives will tell you, like those. Gosh darn it! I'm having the old Square D, the Altivar drives, the Schneider drives. They will tell you what time of day it was, what the ambient temperature was, what the motor temperature was when it tripped. It'll tell you pretty much everything you need to know about the conditions in which caused the fault. And it's got a pretty good interface with it to tell what the codes were and what the faults were. The PowerFlex 40, it just has a code number, F8, fault number 8, and then you have to look it up in the book and see what fault 8 was. So there's a big difference. Always, you're going to need your voltmeter, your voltometer, your fluke meter, let's call it. This one's a really, really good one. The one you guys get is also a really good one. A clamp meter or an amp meter of some sort, preferably a clamp on, is going to be required too. You need to check the current. If you were getting an overcurrent alarm or too high of current or an overload alarm, you need to see and measure the current. If the current doesn't exceed what the overload is set at, but you're still getting an overload alarm, well, then you have a problem with the sensing equipment in the drive. It's not overloading it, it just thinks it is. And that can happen. So you need to be able to check the current. Remember, we do not check current in series with 80 amp lines. We've used a clamp on. So check the DC bus voltage. Like I said, that's going to be the big one. That's going to check. That's going to tell you if your drive is working pretty good. You know what's going on. You know you have voltage coming in. You know you have voltage going out. Check the input diodes if you have access to them. And the problem is most of the time you have to take these drives completely apart to access those diodes. To check the resistors, you have to too. To check the charging contacts, you have to too. Most of these are going to be on the bench, and you have to take the drive completely apart. Therein lies the problem. Like I said, to take these things completely apart and to try to troubleshoot it down to a component level takes forever. I could have already had a new drive put in, and we're back running in the time it takes you to just take the drive completely out and check it. And then are you going to be able to fix it once you've checked it? Probably not. That's why we just say if it's less than 100 horsepower drive, throw it in the trash. And that's why I'm not going to go into deep transistors and check the IGBTs because I do it. So that's pretty much the end of today's lecture. If you have any questions, please feel free to contact me. If not, let's ask some questions of you. What's the one first thing to do when troubleshooting an electrical problem with an AC drive? The first thing is to develop a plan, right? That's usually what I do first. Develop a plan. I plan my dive, I dive my plan. Develop a plan. Once you develop a plan, then you can go do it. You can't just start wandering around and trying to think of things to do. Develop a plan. What should you do next? Well, gather up your tools. You need to have all the tools that you're going to need. A lot of times these things don't occur right next to your toolbox, so you need to gather up all your tools and get them to where you need to go. And make sure that you have all your tools. What should you do next? Well, the next thing I would do is gather up my PPE. What kind of PPE do I need? What kind of experience do I need? Is it in the MCC room? Is it in the high voltage rooms? Where do I need? And what kind of PPE do I need? What next? Do my checks and see what I have. Name some of the testing equipment to use when troubleshooting. Well, voltmeters, ohm meters, amp meters. Those are three pretty good ones. You can use a megometer if you would like. You can use a diode checker if you would like, if you wouldn't go that far. Most of the time, you don't need anything more than your fluke meter, your volt-ohm meter. Check voltage and check continuity. Make sure nothing's shorted out. And if there is, you fix it. If not, then move on. Name some parts of the drive that can be checked. Well, there's a ton of parts on the drive that can be checked. You can check the DC bus, you can check the capacitors, you can check the diodes, you can check the IGBTs. You can check all that, but you have to take the drive apart to check it, and I don't know if you should be checking. Do you need electrical tools to troubleshoot AC drives? Really, you shouldn't need screwdrivers and things like that because most of the stuff is going to be accessible. You might have to have a few basic hand tools. So, but the biggest diagnostic tool you're going to need is your meter. Are you ranking material? I would say so.